What's up, you data friends? It's Yanis here and welcome to my channel. In this video, we're going to show a machine learning linear regression example using Python. And more specifically, we're going to touch on this overview over here. So we're going to start by briefly explaining what is machine learning, the process. We're going to formulate our problem, then we're going to load the raw data. We're going to do data pre-processing, we're going to split the raw data, we're going to run regression, we are going to evaluate our regression, and then we are going to run some additional models in order to compare our regression model with other models, just to see if they perform better. And at the very end, when we run all these steps, just to show you, we are going to export our raw data, and then we are going to create this Power BI dashboard where we can see our predictions. So we have our actuals and our predictions. We can click anywhere and investigate our data. As you can see, everything changes. So this is how I would go about deploying, so showing my results, my predictions to the business. I'm going to have all these files, so everything I have just shown you, and the notebook with the code and without the code in my GitHub page. So I suggest downloading the one without the code and start typing in the code as we go through this tutorial, because this is the best way to learn. And before we start this tutorial, if you're passionate about data analytics and data science, then I would really appreciate it if you click the like button, subscribe to my channel, and enable notifications for my future videos. Right, starting by quickly explaining what is machine learning. So the idea is that we take some raw data, for example, this CSV file. We say to the computer that our dependent variable is this price over here. Then the computer learns from all these data. So what is the relationship of all these variables to price? And then the computer is going to tell us which of these variables are good predictors of price. By the way, this is one example. And it's also going to learn how to make predictions. So if we give the computer new data without this column, without price, then the computer is going to be able to make predictions without really knowing the price of the car, for example. So we take some raw data, we give it to the computer learns from that data, and the computer returns results on that data. Right, moving on, we have the machine learning process. So as a data scientist or a data analyst, if you have a machine learning problem, then most probably you are going to follow this process. And let me go over here so it's clearer. So you're going to start by stating the problem you're trying to solve, whether it's a research question or whether it's a hypothesis you are going to test. Then you need to go and gather all the raw data needed in order to answer that question. Then you're going to start with data pre-processing. So you're going to explore your data, you're going to clean it, aggregate it, transform it, check distributions, normalize it or scale it if needed. You are going to convert your categorical values into numeric representation, and you're also going to do feature selection and feature engineering. Then when you have your raw data ready, you are going to split the raw data into train, test, and evaluation. And the reason we're doing this is so that we can train the model on this 70% of the data. We're going to test the model on this 20% unseen data. And at the end, when we finally select our final model, we are going to use this 10% to evaluate our model at the very end. Here, we are also going to separate our X's and our Y, dependent versus independent variables. Then we are going to need to choose the model that serves our needs. We have regression models, so when we are predicting a continuous number. We have classification models when we are predicting a specific class. We have unsupervised learning models, which is when we don't have a Y variable, we are just investigating relationships and creating clusters. And we also have time series models, is when we are predicting the future values of a time series variable. Then after we select our model, we are going to evaluate our model. So we have specific evaluation metrics depending on the model we select. Then we are going to do parameter tuning. So we're going to adjust the hyperparameters in order to try and improve our model. And we are going to repeat this process until we find the model that gives us the best performance and also the hyperparameters that give us the best performance. And at the end, when we select our model, we are going to test our model on that 10% unseen data, completely unseen data, and then we are going to deploy our model. Right, so as we've said, we want to start with the problem formulation phase. So we're going to go back into our notebook and we are clearly going to state the research questions we are trying to investigate. So we want to understand the factors that affect the car prices. And we also want to be able to predict a car price based on the data or the variables we have. So our raw data, I took this raw data from Kaggle. I'm going to have the link down here, I think. There we go. And I'm also going to have the raw data in my GitHub page so you can download it. So our raw data has information about car prices. So you can see here is the car name. And then we also have information about the car itself. And we also have the price of this car. So what we're trying to do now is to understand what variables out of all these variables impact the car price the most, and also being able to make predictions when we get new cars, so new variables. So imagine we get these new cars now, so all of these new cars without the price. Let's copy it, paste it over here. So if we get this data now, we want to be able to look at this data and say, okay, this Alfa Romeo should be about, I don't know, $15,000. And then this Audi over here should be $20,000 based on the information we have over here. So all of these is going to be done by our machine learning model. Right. Going down to the libraries we're going to use quickly. So we're going to use operating system, Numpy, Pandas, MatPlotLib, Seaborn, and also from sklearn, we're going to use all of these libraries down here, which I'm going to explain further down when we use them. Here, I'm only changing the scientific numbers to float. I'm increasing the size of the plots, and I'm also increasing the number of columns we can see when we print values in Python. So if I click run quickly, so we import our packages and libraries, you can see this is running, it finished, and now we need to load our raw data. So in order to load your raw data, you need to say pd.read CSV, and into these brackets, you need to put the location of your file. So my file is, where is it? I think it's here. This is the file. I can either click on properties and get the path, or I can get the path from here. I can copy this. I can come into Python. I can paste it up until, where is it? Just before the name of the file here. I can click paste. Make sure you use double backspace, or however we call this, every time we separate the folder. And at the end, you need to specify the name of the file. So you can get the name from here. So single click, copy this, and then paste it over here, .csv, and this is going to load our raw data into, okay, what's the error we get? There's no search field. Oh, I have probably moved the file. So if I check the name of my path, I've actually added 1 and 2. So if I added 2 dot, it should work. So this dot, click run. Still not working because 2 dot linear regression. What's wrong with it? Okay, I'm gonna copy the whole thing. So we do this, paste it over here, and then we use double, click run. Now it works. And what I'm doing here is that I am printing the shape. So you can see we have 205 rows and 26 columns. And then I'm also printing the first 5 rows. So dot head and then empty brackets It's going to print the first 5 rows. So we can now see our row data, which is this row data we have in Excel that we have just shown. So this row data over here. Right, going back, the first thing I always do after I load my raw data is to investigate all the elements within each feature. So what this is going to do is that I want to be able to say for every column I have, how many distinct values I have, and also which are those values. So if we go back quickly, what I'm saying here is that I'm saying for column in row data. So this is going to loop through all of our columns. I'm going to create this unique values array, which is basically going to have all the unique values of each column. So it's going to start with car ID, for example, and the unique values of car ID is actually, you can see all of these are unique. So the unique values should be 205 unique values. So this is why we see 205 after we print it. Then I also want to calculate the length of those unique values. So the length is the number of those unique values, not just the actual unique values. And then down here where I have this if, I'm saying that if the length of the unique values is less than 10, then I want you to print the name of the column, the NR, which is the length of the unique values, and the actual unique values we have over here. And just to show you, sorry, I need to cover the else. So the else is saying just print the column and then the length of the unique values. For example, car ID, because we have so many unique values, I don't want to print them. I don't want to actually see them. But for categorical columns, like this one, for example, fuel type or aspiration, I actually want to see what are those unique values. So just to go through quickly, let me run it. You should get the same result as you see. So what this is going to do is going to start with car ID. The car ID unique values, sorry, the length is more than 10. So it's not actually going to print them. It's going to move to the next one. It's actually going to try and do this. It's going to fail. Then it's going to run this one, which is just the column name, and also the length, which is 205. For symboling, however, because the length is 6, it's actually going to run the first thing. And for symboling, you can see the unique values we have is -2, -1, 0, 1, 2, and 3. For car name, you can see we have 147 distinct car names. So what this is telling me, since we have 205 unique IDs, it means we have duplicate car names, but with different IDs. So this is something we need to look at. Fuel type, we have 2 fuel types, diesel and gas. For aspiration, we have 2 types, standard and turbo. For door numbers, we have 2 types, which is the 4 and the 2. For car body, we have convertible, hardtop, hatchback, sedan, and wagon. So you get the idea. I'm investigating what kind of data I have in my data set. So I always start with this query. So I suggest copy this query and paste it every time you start your machine learning project, so you'll be able to view what kind of data you have. Right, the next thing I always do is to check for null values. So as you can see, I'm saying raw data.isNull.sum, but I don't have any null values in our dataset. So very quickly down here, I'm manually creating some null values so I can show you how to deal with them. So if I do plus, and then if I run this quickly, and then run the dot head, so you can see what I'm doing. So copy dot head. So what I did here is that I have created this price to. So I said set this price to equals to the actual price. However, change the first, second, and third value. So first, second, and third value to be equals to an 8. So if I do dot 10, so you can see what it did. Scroll all the way, so you can see all of these is the same. So this price 2. However, I've created some null values in this price 2. The next thing I want to do now is to, so for example, if I wanted to drop those null values, I was going to run this. So let's run it so you can see. So if we run this and we scroll, you can see we don't have those null values anymore. We've dropped the whole line. But if we don't want to drop the whole line and we want to replace it with the average car price, for example, I can run this. So again, I'm going to copy this. I don't want to drop them. I want to update them with the mean price of the cars. So what this is doing is that it's selecting price to column, where price to is null. So those three we've just created. And then it's setting those values, those nulls, into the price to average dot mean. So if I run this quickly, you can see they're going to have the same value. There you go. So the average car price is $13,000 something. So I have just replaced those null values with the average. So this average is actually a way of dealing with null values, just in case you don't want to drop the whole line. Next, what do I have here? I'm just dropping the column price to. So if we run it here, so we're going to run all of this, .head. You can see that if I scroll all the way to the right, we don't have this price to anymore. So I created a new column, I updated with the column with null values, and then I've shown you how to drop the whole line, and also I've shown you how to replace the null values with the average, which is like very common in data science. Right, moving on, we have investigating the numeric values with scatter plots. So after I deal with the null values and investigate my data set, the first thing I do is to visualize my data with scatter plots. So this SNS.pairPlot is the best way of doing it. So I say G equals, I can use any letter, SNS.pairPlot, and I pass the whole data frame. So all of this data frame. Quick note, do not run this on a big data set because it's going to take time. So if I click run now, you can see it's going to take some time to run. But the idea is that first I start with all the data set, then I zoom in and I select the variables that I see a relationship. So I see that as one variable increases, the other variable also increases or decreases. So I'm going to wait until this finishes. There you go, you can see this is done now. So the column I'm mostly interested is price, which is this one down here versus all the numeric variables we have, because this is a scatter plot. As you can see, it's very difficult to read. That's why I said first run all and then zoom in. So this is exactly what I'm doing in the next step. So I can see a few variables here, this one, this one, this one, this one. No, this one not so much. This one, this one, this one, this one, and this one's negatively related. So I'm going to select three. I'm going to select wheelbase, engine size, horsepower, and drive wheel to zoom in and investigate it better so we can see their relationship. I also added hue equals drive wheel. So drive wheel is, which one is it? Let me show you. Drive wheel is this one over here. So drive wheel is telling us if it's a forward drive, a rear wheel drive, and also a four-wheel drive car. So we have three options. That's why you see three different colors, and the colors are here. You can see in drive wheel, rear wheel is the blue, four wheel is the orange, and the green is, sorry, forward wheel drive is the orange, and the green one is the four-wheel drive. So what this is telling me from price to this one, the first one, which is wheelbase, is that as we increase the wheelbase of the car, the price of the car also goes up. Additionally, what is also telling me is that for forward wheel drive cars, they are usually cheaper than the rear wheel drive cars as long as we increase the, what is this one? The wheelbase. And it's kind of similar case with the other two. So this one is the engine size and the horsepower. So as we increase the horsepower, the price of the car also increases. And then from our data set, the rear-wheel drive cars are usually more expensive, as you can see there at the top, versus the four-wheel drive cars. Same case with this one, which is the horsepower. And also we can see the distributions here. So price, wheelbase, and engine size, and also what's this one? Horsepower, price with price. So the distributions over here, you can see that the four-wheel drive cars are usually cheaper and have a lot more than the rear-wheel drive cars. They span the price from here all the way to the most expensive one, which is the 50,000 plus over here. And then for the four-wheel drive cars, the distribution is right here. It's not bad distributions. It's actually because it's on the left and it's a right lean distribution, but we're going to show how to investigate distributions further down. The next thing I want to do now is to add the regression lines on these graphs so I can see the rate of increase. So which one of these drive wheel has the highest rate of increase. So the way to do this now, by the way, we haven't explained the code, sorry. So sns.pairplot, then we select the specific columns we want to create pairs for. Q is the category we want to break it down by, and then height is basically the size of these pair plots. Next, if I want to add the regression line, then I can add a comma and add reg equals, comma, kind equals reg, and this is going to add the regression lines into our pair plots. So you can see here, price to wheelbase is that the rate of increase for forward wheel drive cars, and also the rear wheel is kind of like, not average, but is the same almost. However, for four-wheel drive cars, as you increase the wheelbase, then there is a more drastic increase in the price, because you can see the green line there, it increases way drastically. And it's the same case with this one over here, the engine size. However, for the horsepower, they pretty much follow the same rate of increase. So these variables, all of them are like good predictors of the price of the cars, but they have different rates of increase. So the coefficients that we are going to investigate later on. Right, moving on, we want to further investigate now one single pair. So I'm going to select the price and the horsepower, so this pair plot, and break it down further more. So down here, this visual is investigating the relationship between price and horsepower. However, we are breaking this down by car body and also fuel type. So in order to do this, we need to say sns.scatterplot. Our x is going to be the horsepower, which is this one over here. Our y is going to be the price over here. Our data is going to come from our raw data frame. The color is going to be green. Actually, we don't need the color because I'm breaking it down into different colors. So it's not going to be a single color. So I can actually remove this and it's still going to work. So let me quickly run this so you can view it. We can see we've changed colors now, but if I remove this, it's not going to make any difference. There you go. Our hue is going to be car body. So car body is these categories we have over here: sedan, wagon, hatchback, hardtop, and convertible. And our style, we're going to have the fuel type, whether it's gas or diesel. Then size S equals 90 is the size of our plot. So now we can start investigating this plot and see if we can get any insights. So the first thing I get straight away is that the hatchback cars tend to be on average less expensive. So you can see the green circles over here, and the regression line, it was going to be something like this. It was going to be an easy regression over here. By the way, I don't have the regression lines because it's going to be a mess. We have a lot of categories. Then for the sedans, I can see that as we increase the horsepower, so the blue ones, there is a much higher rate of increase because the regression line was going to be something like this. So the price of the car was going to increase way more than the hatchbacks as we increase their horsepower. Next, what I can see is that almost all hatchbacks are gas because they are almost all circles. Then the hardtops tend to be more expensive as we see over here. Actually, there's two more over here, so there must be some reason why those are cheaper. Then the sedans are the ones that are usually diesel. So as you can see, the X's are mostly blues, and we also have like one red over here and then some oranges down here. And then I think that's all I get from this graph. So again, it's another way of further zooming in and investigating relationships before you move on with your predictions so you can understand your data set. What do we have next? So now we want to investigate our categorical data. So we've done the numerics. So these scatter plots are for numeric data. Now we're going to go into categorical data. And the first thing I want to see is the average price by car body. In order to do this, I'm going to use a pair plot. So SNS.pairPlot. My X is going to be the car body. So car body, you can see the X over here. My Y is going to be the price over here. The data is going to come from our raw data frame. And I also want to plot the labels. So these numbers over here. So I need to say ax.bar labels, ax.containers, and then the first value. So this was recently added actually in the SNS.pairPlots. So quick notes is that the lines signify the confidence interval. So these lines give us the confidence interval. And also when I run these SNS.bar plots, it takes the mean by default. I've also calculated the mean down here just to be able to compare the means, just to make sure it's correct. So for convertibles, the average price of the car is 21,890. So 21, where are convertibles? 21,890. So you can see the mean is actually correct. For hatchbacks is 10,000, sedans is 14, wagon 12, and then hardtop is 22,208. So what this is telling me now is that when we get a hatchback car, most probably is going to be in this range of price. Or when we get a wagon, for example, it's going to be slightly higher. When we get a sedan, it's going to be again slightly higher, the average price. Or when we get convertibles or hardtops, then they can actually be more expensive. Right, next I want to take this code now, so what we've done, and investigate the relationship between price and every single categorical column we have. So what I did down here in the next piece of code is that I have created this categories list, and I've listed all the categorical variables. So we have car body, aspiration, door number, drive wheel, engine location, fuel system, engine type, and cylinder number. Then I've set the size of my plot, and I've set the size into 8,5. So it's going to be about this big, as you see down here. And then I created this for loop where it's going to start with the first category, which is car body. It's going to plot a bar plot, so it's the same plot as above here. So I can actually copy the whole thing and paste it down here. The only change I've done is that for my X, I've set my X equals C, and this C is going to be the category. It's going to start with, the car body. So it's going to start with car body, and then it's going to move to the rest. My data is coming from my raw data frame, and I've also disabled the confidence interval, so this line over here. For my data labels, I have to say for container in ax.containers, then I want to plot the container of the first category, and then plt.title equals, plt.title, then it's going to be C, which is going to be the category. So it's going to start with car body, and then plt.show to show the plot. So if we scroll through these codes, so let me run it first, and then we scroll through it. So the first one, which is the relationship between car body and price, we've actually done. So it's this one. Then we have the aspiration. So we can see that on average, turbo cars are higher in price. Then we have the door number, so not much here. Then we have the drive wheel, so clearly the rear wheel cars are more expensive on average. Then we have the engine location, so this is telling us that if the engine is on the rear of the car, then the average price of the car is significantly more expensive. Then we have the fuel system, so there is a lot here, but the most expensive fuel system is this MPFI. We can see on average is $17,829. Then we have the engine type, so this engine is the most expensive on average, followed by this engine. I don't know these engines. Then we have the cylinder number. So we can see if we have 2 and 3 cylinders, then on average is the cheapest cars. But when we have 8 and 12 cylinders, then on average the price of the car is going to be more expensive. So again, we get a lot of insights by running this code. Next, we want to investigate our distributions with distplots. So to do this, I'm going to start with the distribution of price, which is our dependent variable, which is the one we are going to try and predict later on with our machine learning model. Then I need to say x equals raw data.price.value. So this is going to pass the price into this x array. And then I need to say sns.distplot, pass this array, set the color to blue. And then I also want to calculate the average of the price. So mean equals raw data price.mean. So I'm going to store the average car price into this mean object over here. And then I'm going to plot the mean by saying plt.axv line mean. So pass the mean 0 to 1, and then the color equals red. So if I run it, it's going to be the same distplot. So we have the distribution of price, which means on average, we're going to have lower car prices, and then we also have some higher car prices, which are these ones over here. The next thing I want to do is to run exactly the same code, but for all numeric columns, which is similar to what we've done up here. First, we create one, and then we recreate this one for all categorical columns. Down here, first I create one for my numeric price column, and now I'm going to write this for loop, which is going to go through all of our numeric columns. In order to do this, first I'm going to identify all the numeric columns. So I don't want to paste them manually as we've done before because we have a lot. So if I create this list first, and then if I run this raw data.select data types, and then include only these numerics from this list dot columns, then this n variable, if I run it quickly, and then if I run the n variable, so you can see, is going to be a list with all of our numeric columns. There you go. You can see all of these columns are actually numeric. Then I want to set the size. So we've done this before. And then I want to take this calculation as is, all of it, copy it, paste it in our for loop. And the only change now is that from our raw data, I want to take the n values, and n is going to be my first column, which is going to be car ID. So x is going to be only the car ID values. Then I plot my x, and then I calculate my average for my n. and it's going to be again the average of car ID. By the way, car ID doesn't make any sense to calculate the average, but it's just there because it's a number, it's a numeric column. And then I also plot my mean. So it's exactly the same code as above here. We just adjust it so it's gonna change every time we loop through. So if I run it now, we can see we start with car ID, then we have the distribution of symboling, then we have the distribution of wheelbase, car length, car width. So if I scroll through all of these distributions, you can see there is no crazy distribution here. I mean, this one maybe, but it's not as bad. There is a reason why we have this, is the high compression ratio cars. Then we have the horsepower, peak RPM, so good distributions. So yeah, so there is nothing crazy in our distribution, so I don't want to take any actions up until now. Right, moving on, another way of investigating the distribution and also the outliers is box plots. So a box plot is this plot over here, which is a good way of quickly fleshing out mathematically the outliers. In order to do this, we need to say x equals raw data price dot values. So we save this array into x, and then we pass this x array into our SNS.boxplot. And if we run this, we can see this box plot over here. I have also printed the median because this line over here is the median value for price in our dataset. So just to go over these nodes quickly, the line signifies the median. The box in the middle shows the beginning of quartile 1, which is the 25th percentile, and the end of the quartile 3, which is the 75th percentile. The whiskers left to right show the minimum quartile and the maximum quartile, and then the dots on the right are the outliers. We can also have outliers from the left-hand side. However, in our case, because we have done a lot of investigation in our dataset, and there is actually reasons why these prices are so high. For example, you remember when we were checking the engine power with the price or the horsepower with the price. So these car prices, these dots, these outliers are actually such a high price because they have very high horsepower. So I don't really want to exclude them. If you want to read more about these box plots, you can follow this link so you can understand them better. And the next thing I did over here is that I want to repeat this box plot, so this code. However, instead of having just price, I want to loop through all of our numeric columns, which is exactly what we've done before. So we can copy this, we can paste it over here. We can change this price that we had before into our C, and C is going to be all the columns in our numeric variables, and these numeric variables is basically these numeric variables which we created in the step before. So if we run this quickly, you can see that we get the distribution, so the box plots of every single numeric variable. So we have symboling, we have wheelbase, 2 outliers, we have the car length. You can see there is 1 outlier from the other side this time, and we can investigate all of this. So you can see for compression, there is a few outliers way out, so that's something we could look into further more. Then we have the horsepower, we have the peak RPM, CT. Yeah, we have a few outliers here and there, so price is the last one. But because of all the investigation we've done before, I don't want to exclude any outlier just yet. The next thing I wanted to show you now is to investigate the distribution of price by categorical variables by data points. So now we can use these these box plots, but by category now versus the price. In order to do this, first we need all the categorical variables as we've done over here. Then we set the size, and then in our SNS.boxplot, our X is going to be the first category. So you can see it's going to start with car body. our y is going to be the price. So before, in our box plots, if you see, we only had our x. We didn't have a y, only x. It was one variable, numeric, per time. Now we also have x and y because we want to investigate the data by price and category. And these are all the categories. So y is always going to be price. Data is going to come from raw data, and the color, so this one is the yellow, and then the swarm plot is actually all these dots you see. You see all these dots? This is a swarm plot. So I want to also overlay on top of my box plot a swarm plot that's going to take exactly the same values, but it's not going to be a box plot. It's actually going to be all the dots. And the color of this one is going to be red. So if I run this quickly, you can see these box plots now are broken down by categories, starting with car body, and we can also see these outliers. They are over here in sedans, in hatchbacks. These are not outliers. This is an outlier in wagon, and we can keep scrolling. We have aspiration, we have the door numbers, we have the drive wheel. So I don't really see anything out of the ordinary here. Right, moving to the next stage now, which is converting the categorical values into numeric representation. This is actually very common practice in data science and machine learning, just because if you have text like gas or here standard, what's that, standard or door number equals 2, it's not actually a number, it's text. So we cannot apply maths on it. So we need to somehow convert these categorical variables into numbers where we can apply maths on them. And one of the most common strategies is this pd.getDummies, and into columns we specify the categorical columns we want to turn into numeric values. So all of these are our categorical columns that we want to make them values. And what this is going to do, if we run just that, is going to take these, so give me a sec, let me put it here and run it and visualize it so you can see. It's going to take all these columns and the values within these columns and switch them to zeros and ones. So let's start with the first example. Let's start with the, what's the first one? We have fuel type is going to be the first one. So if I scroll all the way to the right, actually we started with car body. So we're going to do car body. So it's going to split out this column into all the possible values within car body. I think it's 5 different car bodies, which is the convertible, the hardtop, the hatchback, the sedan, the wagon, and the wagon. And it's going to put zeros and ones depending on the value we have over here. So here in the first line, we have a convertible car. So we're going to add 1 into the convertible and zeros on the rest. Then in the second line, we have a convertible car again. So we're going to add 1 and zeros. In the third line, we have a hatchback. So we're going to put 1 under hatchback and zeros on the rest. And it's going to go on, etc., etc. It's going to repeat the same process for aspiration. As you can see, we have aspiration standard or turbo, zeros and ones. We have the door number after, which is 4, 2, zeros and ones. We have the drive wheel, which is the wheel, the forward wheel, and the rear wheel, again zeros and ones. So by running this code, we are turning all of our categorical variables into numeric representation. So now we can apply calculations on them. The next thing I did is that for cylinder number, because each time we increase the cylinders, 2, 3, 4, there is a logical sequence, there is actually a scale. So I'm manually changing those into numbers. The reason we do this is because we want to say, as we increase the cylinder number, do we increase or decrease the price, which is what we have actually identified in our exploratory data analysis phase before. The reason we don't have this method on car body, for example, it's because it's not like we can say after convertible, you're going to move to hardtop, and after hardtop, the next stage is hatchback. It could be random. It's completely random. It's a category. So there is no sequence. But for cylinder number, because there is a sequence and because it was categories, now we are switching them into numbers. So all I'm doing here is that I'm saying when the cylinder number equals 2, then set the cylinder number to 2 as a number. And at the very end, I'm converting all these columns into an integer column. And if we run this quickly and we investigate the data types, you can see that the only data type we have that it's not a number, it's this object over here, which is the car name. Everything else now, it's been turned into numbers, and we can actually feed this in our machine learning algorithms. Right, moving on, the next step is to select the most important features in order to use those into our algorithm. And there is usually two things I do in this step. The first one is the correlation coefficient, this heat map you see over here. And the second one is the feature importance, which I'm going to show you later on. Right, starting for this correlation coefficient, the first thing we need to do is to create a data set to display on a heat map. We will use a correlation data set, which I'm also going to run it so you can see it. We need to run .core and then the brackets into that data set, which is this over here, and the method is Pearson, to find the pairwise correlation of all columns in the data frame. Any null values are automatically excluded. The closer to 1 or minus 1, the better. So after we run this correlation, it's going to give us a number, and that number is going to range between 1 to minus 1. And the closer that number is to 1 or minus 1, then the better, the higher the relationship of those two variables. And then as one variable increases, the other variable tends to also increase or decrease based on that number we're going to get for the correlation. And you can also read more about this correlation over here. So let me quickly run this. Actually, we're going to get an error because I've already run it and I cannot delete again the card name. So if I run this, it should work. There we go. Let's start from here. The first thing, we set the figure size. So this is our size. Next, we need to specify the variables we want to run correlation on. We can actually select the whole data set, but because I have a lot of zeros and one variables that we have just created in this above step, I don't want to include these ones because it's just zeros and ones. They're not going to add anything. So I select all the numeric variables over here. Then I'm running this correlation on just these numeric variables. So this is the whole data set. And then I select only these columns. And then I run this dot correlation, and then I'm setting the method into Pearson correlation. So if I run this quickly, this is actually going to be the correlation data set that we set before. So this is a correlation data set. It tells you the relationship between car ID and car ID is 1. And this is because as one goes up, the other goes up. It's the same variable, that's why. And this is always going to be 1 for all the same variables when comparing them with each other. So you can see 1, 1, 1, 1, 1, 1, and it's going to go on and on and on. And this is telling us the relationship, for example, if we go down to price, the relationship of price and symboling, it's not important. It's not close to 1 or minus 1. This is 0.57 to some extent. This is 0.67, so this is higher. This is actually a good relationship, card width with price. So as card width increases, price increases by 0.75 respectively, so with 1 unit of change. Right, the next thing we want to do is to run this heat map. So sns.heatmap, I want to pass this correlation data set we have just created. I want the annotations I also want to plot the y tickers. So these y tickers is these columns, and this is going to be the columns. So our calls is actually these n variables, which is actually this one over here. Our x tick labels, which is these ones, they are the same. Then I want the size of these numbers to be 10, and I want the CMAP to be green. We have actually shown a lot of different examples in the previous tutorials, which was in Seaborn tutorials, I think. Let me see if I can find them. Yeah, there we go. So we have the blues, the greens. Let's try the blues. So this one over here. Let's run this one, run it. There we go, we can see it's blue now. And just to quickly investigate price, which is the one we are interested the most, which is this line or this line, they are the same. We can see that price with this highway MPG, they have a negative correlation of 0.7, which is quite good. But the highest one is actually this positive correlation between engine size and price. So as we increase the engine size, then price changes respectively by 0.87 to that 1 unit of change. The next highest correlation is this curve weight, 0.84. We have 0.76. So we can start picking now all the important variables. We can identify the important variables on a one-to-one relationship. Now, if we don't want to have a one-to-one relationship, we can actually run this feature importances method, which is not exactly a one-to-one relationship. So this feature importance method is going to give you a score per variable, assuming we use all the variables. So we actually need to use all the variables. Then we get the prediction, and then we get a score per variable that affects the most or the least that prediction. So if you want to read more, I have linked this article down here, which goes into depth about how feature importance or entropy is calculated and how to interpret it. Right, in order to run feature importance now, first we have to split the raw data into x and y. So our x is going to be all the variables in a Numpy array excluding price. These x underscore columns, I think I don't use it here, I use it later on. And then our y is just going to be the price. So if we view them quickly, our x is a Numpy array of 205 rows and then 47 columns, which it was before a data frame. Where is it? This is the data frame. Now it's a Numpy array because machine learning models only accept arrays. Our y variable is the price, so it's a one-dimensional array, just the price, as you see over here. And then the next thing we have to do is to actually run a decision tree classifier and feed our x and our y. So I call a tree-based estimator here. This is just a simple decision tree. We can actually run it on random forest and other trees. I set the random state equals to 15. The criterion is entropy because that's what we want to calculate, information gain, and the max depth equals 10. If you want to read more about decision trees, then you can follow these links over here. Now, after feeding this, so I think I've actually run this, the next thing we want to do is to get the information gain, the feature importance, which is the information gain, which you can actually get by running this dt.featureImportances. So if I run it quickly, before I show you how I've done it down there, so if I copy it, paste it here, and then I run it, then we actually get the feature importance per those 47 different variables. So if you count these numbers, they're going to be 47. So that's 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6, 7. That's 42, 43, 44, 45, 46, 47. Then what else we can do is that we can actually visualize the whole tree to understand how this works. So before I try and explain this, let's get the feature importance first per variable so we can actually view it. So I'm going to run it down here. What this does is says that for I, column in enumerate our data frame minus the price, then I want to print the feature importance of the first column, and then this feature importance is going to be the dt dot, which is the data tree, which is which one? This one over here, dot feature importance I, which is going to be the first column, print the feature importance, and also create a data frame. So these, I'm creating a data frame and I'm saving my results. And down here, I try the first time to concatenate the previous results with the new results. So the first time we run this is going to fail, so it's going to move down here. But the second time and then going forward is going to insert new data into this data frame that you see over here. And because I've run it twice now, I have 2 indexes. If I run it again, I think I'm going to have 3. Oh, it throws me an error. So I think I need to go back into here and rerun it quickly. Rerun this feature importances. This is our tree, which I'm going to try and explain. So you see here, it gives us the feature importance for car ID 0.067, which is this first number over here. And then we move on into symboling, wheelbase, etc., etc. And then if I scroll down here, okay, the first time I actually have to draw it and then recreate it. Because if I run it twice, then that data frame is already created. That's why I threw the error, but now it's fine. And then if we scroll down here, we get the variable and then the feature importance. And this is also sorted by ascending, so the highest to the lowest. And to try and explain this now, if we go back into this tree, so this is our tree. Let's see if we can make this smaller. So let me see, this is graph source. Can I make this smaller? So I think if I go at the top, and then if we make this maybe 5 by 5, and then we run it. Did I run it? Yep. And then if we go down to our tree again, which is this one, and then if we rerun it, is it going to be smaller? No, well, it is smaller, but it's still very big because we have so many different variables. Anyway, let's try and explain it. So the variable with the highest feature importance is kerp weight. And the way it's going to be broken down until we arrive at a price, we say if it's less or equal 2417, then it's going to go value if true on the left. So if we scroll, keep scrolling on the left, we can see, yep, true value. And then value if false is going to move to the other way. Then the second highest feature the second highest variable is going to be the wheelbase. So if the wheelbase is less or equals 9.5, and let's see, the wheelbase is actually down here because probably the second one is the car height on the value if false. Let's see if we can find it. Value if false. Keep scrolling. Oh, this is so difficult. Yeah, there we go. Car height is actually the second one. It has a higher entropy. So if it's false, then we have the value if true down here, and then the value if false down here. And it's going to keep breaking the data like this, variable by variable, until we go all the way down here where we make our predictions. So class is actually the price of the car, and this is where we get, after we finish with all the different separations, we arrive down here, which is our prediction. And this is how feature importance is calculated. So we can see kerp weight is actually the most important feature based on this model we have just run, and then car height. But before, if you check on the one-to-one correlation, it was not this kerp weight. It was actually the engine size. On a one-to-one correlation is engine size, but on feature importances that uses all is actually this kerp weight, which is second in the one-to-one correlation. So horsepower is down here, but the engine size is actually number 6 on the feature importance, and is actually number 1 on the correlation coefficient matrix. So these are 2 very good ways of identifying the most important features before you go on and run your machine learning models. Because usually the first thing we do is that we include all data, and then we want to improve our results. We minimize the data to the most important features. Right, we are 1 hour in this video and we still haven't managed to run our linear regression, and this goes to show that most of the time as a data scientist or a data analyst, you will be cleaning and investigating the data versus running your machine learning models. And if you've made it this far, please click the like button and make sure you subscribe to my channel. Right, so the next thing we're going to do is to split our raw data before we run our machine learning model. And the way to do this is by using this train_test_split function, which takes as inputs our x and y we created before. So x is our variables and y is just the price. We want to set the training size to 80% of x, and then the rest 20% is going to be my y. And if I run this quickly, you can see that we have 164 rows in my X train, which we are going to use to train our machine learning model, and 47 different columns, which are our variables. For our X test, and this is what we're going to use to test our model. So this is going to be unseen data. We are not going to train our machine learning model on this data set. And then Y train has 164 prices for this data set, and Y test has 41 different prices for this data set over here. Right, so what is regression quickly before we run it? So linear regression is a widely used machine learning model that predicts continuous numbers as outputs, so not classes. It models the relationship of 2+ variables by feeding a linear equation to observe data. In linear regression, you have one dependent variable, in our case is price, and 1+ independent variables, which is our x's. Before you attempt to model the data, you should check if there is a relationship between the variables first. A good way to do this is by using scatter plots to visualize the data. And this is very important because in this case here, all of these 4 linear regression models have identical means, standard deviation, variances, correlations, and regression lines. So the R-squared for all of these ones was probably going to be around 80 to 90%, so very similar and very high. However, only this example shows a relationship. This one, you can see that there is diminishing returns. This one, you can see there is a massive outlier there that we should have excluded if we had any. And this one, there is no relationship whatsoever, but because of the structure of the data, it skews the means, the standard deviation, the variances, the correlations, and the regressions. So you're going to get like a 90% R-squared on this one, but there is no relationship. So it's not a good model. So always make sure you go through the EDA phase before you run your models. Right, going down here, a measurement of a relationship between 2 variables is the correlation coefficient. So we've covered this above. However, even if there seems to be a relationship, you should always be careful when modeling the relationship between 2 variables, as correlation is not causation. The mathematical equation of linear regression is y equals a plus b times x, where x is the independent variable. So this is going to be x plus all other independent variables. Our y is the price, is the dependent variable. B is the slope line, so B this one over here, and A is our intercept or our constant, where x equals 0. The most common cost function now used in linear regression is the least square errors function, which is the sum of square errors. And in order to calculate these least square errors, first you must calculate the difference between your actual prices minus the predicted prices. This is going to give us the difference, which is the residuals. And then in order to find the least square error, you will have to find the optimal parameter values, our B, that minimizes the sum of square errors. And this is how it works. We have our dotted lines. We start with the first line. We calculate all the red dotted lines, which is our residuals. And then we get a number. Then we move to the right or the left. We recalculate our sum of square errors. If it's less, we keep moving towards the direction that is less until we find the line of best fit. Right, and in order to run our linear regression model, so all this work we've done beforehand, what we have to do is that first we have to call it LM equals linear regression, and we want to fit the intercept equals true, and then we want to fit this model into our X train and Y train that we've created above, and then we also want to make predictions, so Y predictions equals LM, which is our model, dot predict, and then predict all the values for X train. So if I run this quickly, and then if I run our predictions, so these values, these prices are our predictions, and our actuals is actually this one over here. So this was the actual, and this was the prediction, this was the actual, this was the prediction. And in order to evaluate our model now, we're going to calculate the difference between the actuals and the predictions. So if I remove this quickly, and then if we run this, so we start by printing the accuracy. Accuracy is the R square. So first I'm going to print the accuracy on the training data set, and I need to type in lm.score X train and then Y train, and then I'm going to print the accuracy on the training data set. R2 square, actually these two, they do the same thing. Y train and then Y predict. So we've printed this. So the accuracy on the training data set is 93%, and then the accuracy on the training, sorry, this is not the training, this is Y train, Y predict, the accuracy on the, what's different here? So Y train, Y train, Y train, okay, the accuracy on the training data set prediction, there we go, because this is the Y predict, is the 93%. Then the accuracy on the testing data set, which is this one over here. So this is data that the model has never seen before, and I'm making predictions and then evaluating it, because if you remember, we have actually trained the model on X train, not X test. So X test, the model has never seen before, and it actually managed to get 85%. Now the other two is the root mean square error, which is the most important when running a linear regression, for me at least anyway, because this is the average error we get. And in order to do this, we need to type in a square, open brackets, mean square error of the Y train and the Y predict, and also the mean square error of the Y test, and then the predictions on that test. So I'm using the test, I'm making predictions, and then I'm cross-checking them on the actuals of the test. And if we see down here, the root mean square error on the training data set is $1,943. So this is data that we have trained the model on. And then the root mean square error of the testing data set is $3,224. So you can see it's worse because the model has never seen this data before. That's why we leave some data out so we can really test the model. So this is telling me that on average, on future predictions of cars, I'm going to be about $3,200 out on the actual price. So what we want to do now is to try and minimize this root mean square error on the test data set as much as possible. And this is the mean absolute error, which is down here. I'm also printing the coefficient and the intercept in case we want them. So that's the coefficients. So these are the coefficients per variable. And this is the intercept, which is always going to be constant at the start of our equation. Some notes we have down here is that the accuracy represents the coefficient of determination, so our R square. R square is a measurement of how close the data are to the fitted regression line. In this case, we can say that our model explains 90% of the training data and 82% of the testing data. So that's the 93%, and then that's 85 actually. I don't know why I say 83. Maybe it changes if I rerun. And the root mean square error is the standard deviation of the residuals. Residuals is the difference between the actual and the predicted. Hence, the root mean square error is a measurement of how spread your residuals are. The mean absolute error is the average of all the absolute errors. So I take all the errors, which is all the red lines, and then I average them. What else do we have? Coefficients are the weights, and then the intercept is the expected mean value of y when the x is 0. Right, so after we run our first model and we evaluate it, so we get the root mean square error on the testing dataset, which is the value I'm going to look in this tutorial the most, then we need to find ways of improving that value. When I say improving, is minimizing that value as much as possible. So we're going to try a few methods. Some of them is with less variables, others is with the recursive feature elimination phase, and we also going to try a few different variables like random forest, XGBoost, neural nets, and then we're going to find the best model and then export it and then create this Power BI dashboard from scratch, which has our results. However, I'm going to leave all these in the next video. So I hope you've enjoyed this video and you've gained enough value out of this video. If you feel like you did, then please click the like button, subscribe to my channel, enable notifications, and also try and share it with your friends because I think it's going to add a lot of value to them. If you have any questions or any notes, then please let me know in the comments below. Otherwise, thank you very much for watching this video, and I'm going to see you in the next video.